Thank you very much. Thank you for having me. I'm excited to be at the Journées Arithmétiques at this beautiful and stimulating campus and the largest number theory gathering in the world. And it is a privilege to be a part of this event. I'm looking forward to an exhilarating week. I will touch upon the same topic about an axiomatic characterization of L functions, although in a very restricted setting, but partly my talk will be a survey on the method of the subtitle. So I have also the subtitle of the Arithmetic Algebraization method after the power series case, because the next case we imagine is the case of Dirichlet series, which we want to, which would be ultimately L functions. And a lot of these ideas have very easy prototypes. So the first thing I will remind you of, I will highlight so what is the tenor of the method is that under sufficient analyticity in various settings, which include an arithmetic dimension as well, they imply more analyticity, and ultimately that the formal object was algebraic in nature. And the simplest such theorem is perhaps the removable singularities theorem in complex analysis. So I showcase the simple proof of Cauchy's theorem because the method of a multiplier function and this simple idea will be reflected in the arguments that we'll come to. So this is stating that I use this notation for the ring of bounded holomorphic functions on a punctured Riemann surface equals, so the functions extend through the puncture. Without loss of generality, of course, the surface can be assumed to be the disk punctured at the origin. And so how do we show that a holomorphic function from the punctured disk to the disk extends through the origin? We have this auxiliary multiplier h, in this trivial case, just h of z equals z, which is small at the singular set, just the puncture. And then the multiplier h times f certainly extends as a continuous function, setting the value to be 0. And it is holomorphic because by Morera's theorem, the holomorphic reduces to basic contour integral equal to 0, and we can estimate the integral by a pointwise integrand estimation in the Cauchy theorem using an arbitrary radius of epsilon, then setting epsilon equal to 0. So the second model theorem is the existence theorem of Riemann, which in one basic form states that the category of compact Riemann surfaces with morphisms, the holomorphic maps of Riemann surfaces, is equivalent to smooth projective complex algebraic curves, and the morphisms also algebraize to morphisms of varieties. The notion of capacitance, so basically let me ask a basic question. In the removable singularity theorem, what is the general form of a set E through which we have this automatic analytic extension, so that for bounded holomorphic functions in a neighborhood of E, say this is for Riemann surface case, and then the answer, it has a simple answer in terms of capacitance. So these are exactly the sets invisible to bounded holomorphic functions. Those are exactly the sets of capacity equal to 0. This condition, of course, has multiple equivalent expressions, and we have, let's say, consider the case of the projective line and E a subset of the complex plane. Then the capacity of E is the transfinite diameter defined by this formula, and also equal to the Chebyshev constant of the set in terms of monic polynomials with small supremum and their exponential growth rate. And so this zero capacitance statement, thinking of the previous scheme of proof, it amounts to the existence of a sequence of multiplier monic polynomials with small supremum on H. And we can see, so let me state a combination of the two theorems in a case. in this situation with S equal to the projective line over C and a compact in C, we have firstly extension through E of the bounded holomorphic functions. And I actually maybe apologize, maybe this should have fraction field of these rings, and that would be the field of functions of bounded Nevalina characteristic equal to meromorphic functions on P1, which are just the rational functions of X from the formal theorem that for any set E is equivalent to capacitance of E equal to 0. So here I will switch momentarily to the arithmetic version of this theorem. But how can we use this multiplier H? There are multiple parameters here that I don't want to get bogged down in the technicalities of the limit, but if we have a non-zero monic polynomial H, which is very small on the compact, and then we can, we were basically trying to show that a sufficiently high power of this polynomial times the function expressed at infinity is a polynomial so that it has, okay, I will have rational coefficients in a moment. This should be C here. And okay, so this sequence, this statement of rationality states simply that for large enough power, all the negative coefficients, negative order coefficients of this function should be 0. But these coefficients can be expressed as contour integrals with a small integrand. So let me instead suppose this arithmetic dimension, and I'm proving for you Poyar's theorem, Poyar's arithmetic rationality theorem in this special case. So here the statement is about a formal power series with integer coefficients expanded at the infinity of the projective line, which also defines by analytic continuation. So these German functions extends analytically to a single-valued holomorphic function on the complement of E in the sphere. And suppose that there exists an integer polynomial H, which is not zero, which is not 0, and has supremum smaller than 1 in magnitude on the set E. Here, gamma is a contour that goes tightly around E. So by shrinking this contour, I can assume the integrand is very small, so that this H is less than 1. And for sufficiently high exponent M, we can see that these coefficients, that are some linear combinations. So basically, by Cauchy's formula, for any monic polynomial H, this is one way of viewing the coefficients of the function f. But they are integers by assumption, and also the integrand is bounded by 1 in absolute value for sufficiently large M. And so all of these coefficients will vanish by the product formula colliding with the integrality and like a small integrand. And they prove the rationality of this function, and indeed a bit more than this. And here is a version recently slightly refined in the theory of formal analytic arithmetic surfaces of Bost and Shah of the Poyar theorem from the 1920s. So it states it's very similar to the previous analytic theorem, but replace, if we add the integrality of the coefficients of the formal function, we replace capacitance equal to 0 by capacity less than 1. So this is saying, but this statement has more content. So if we take the fraction fields intersected with the fraction field of the integer power series ring, and the refinement gives the exact equality with the field of rational functions under this condition that E is small. And so we've come to this notion of the transfinite diameter or capacity for the right way to measure the size of a set for automatic extension of a holomorphic function through that set under integral conditions. This theorem has a complement about integrality. You see in the proof, basically, of Poyar's theorem, we have this finitely many possibilities for the poles of these rational functions, coming from a single auxiliary polynomial H. And so it turns out that without the fractional fields, the ring of holomorphic functions on what would be called a formal analytic arithmetic surface attached to basically this way of gluing a Riemann surface with a formal scheme so that I can view the regular functions on this object, like this intersection, and the rational functions, the meromorphic functions of this object as that intersection. So the regular ring of regular functions is, in fact, a finitely generated Z algebra, more than just like having with fraction field Q of X. It is also effectively computable in a broader setting, and that is much of the content in the recent monograph of Bost and Schar on this subject. So here are some examples. Of course, that's the trivial statement saying that if you write down a power series, your coefficients are integer, then if it defines an entire holomorphic function, it has to be a polynomial for obvious integrality reasons. Here's a slightly less obvious example that we have the integral module. So basically, the functions which continue analytically on a slit plane from 1 to infinity and have integer coefficients are exactly the polynomials in x on 1 over 1 minus x. There are finitely many generators. And if we increase that slit to 1/2, we still get a slightly bigger finitely generated Z algebra. And there is a limit to where we can increase the slit because the slit, so the interval of length 4, if you take the reciprocal of this slit, that's the interval 0 to 4, you notice that there was a 1 over x center in the statement of the theorem, and the reduction basically inverts the compact E, and the capacitance, the transfinite diameter of an interval is 1/4 of its length. So this is a case where we have continuum many such formal functions, and it's a borderline of these criteria. So applications of these, so let's go back to the very basic Poyat theorem, of course, that had a prototype in Émile Borel's theorem about meromorphic functions with integer coefficients that converge, that are meromorphic on a disk of radius higher than 1 are rational functions. And the first historic proof of the rationality of the zeta function of any variety over a finite field in complete generality, even before the Eladic cohomology formalism was worked out sufficiently for this, was due to Dwork in 1959, where the p-adic version of the criterion was used. And basically, the zeta function of the variety is a function of q to the minus s. So it's essentially a power series that we're trying to show is rational. Power series, like generally any L functions from motivic origin, that basically should come from a variety, will by design have integer coefficients. So that feature is automatic. And Dwork's analysis expressed the function as a quotient of two convergent entire p-adic power series, and also it has a positive convergence radius. So this contains or abstracts this rationality proof into the Borel-Dwork's criterion. Let me comment where I want to be headed eventually. So power series are a very special case of Dirichlet series when the frequencies are sparse, so supported on a given prime power. And of course, the Dirichlet series generally means something even more general. And so the sparse Dirichlet series, those for which this inf of this condition of sparseness is similar enough to polynomials. For example, you have, so for any Dirichlet series, if you look at its half plane rather than circle, right, the half plane of absolute convergence, and there has to be a singularity that stops at the absolute convergence if the series is sparse, exactly in this sense. So there is a singularity on the borderline of the absolute convergence region as for power series. And of course, that's completely true for L functions. Say, take any non-principal L functions. There's this mechanism by modularity, which gives the analytic continuation. And there is no singularity on the real part of S equals 1. Other than, of course, there is the useful, famous Landau lemma. Then when we have non-negative Dirichlet series coefficients, then the abscissa of absolute convergence is such a pole. was used, for example, in the proof of Bayes' conjecture in some elementary analog of that. A second application to something apparently completely different is a theorem of Salem. So I'm stating a cognate criterion, which is not exactly what we, not contained in Poyas. It contains it for the case of the disk, so it's something slightly different. I haven't proved for you, but the proof is somehow specific to the disk, and is based, of course, on showing that in one form or another, we can view rationality as the statement that these Hankel determinants formed by the coefficients of the formal function are small. So if they are small and they're integers, they have to vanish eventually. That's a criterion for rationality, and the way this is proved is by using Parseval. Okay, so think of the special case where you don't have the fraction field, then it's a completely obvious statement. If you have a bounded holomorphic function on the disk, you integrate then the L2 norm is the sum of the squares of the Dirichlet series of the power series coefficients, and so all but finally many of them should be zero, more or less. One extends this phenomenon to the fraction field, and the fraction. So this is the unit disk, so it's on the borderline of the usual criterion, and these are the field of functions complex analytically that have bounded Nevalina characteristics. So for example, for homomorphic functions, this is a statement equivalent to the finiteness of the Nevalina characteristic, like integral of log plus of the absolute value of the function as the radius approaches 1. And as a corollary, so the reason that Salem devised such a criterion was to show that the Poisson numbers are closed, a closed subset of the interval 1 to infinity, in particular, disproving, so actually proving a conjecture of Vijaya Raghavan that perhaps he was pretty much alone in this belief that at the time that the Poisson numbers are have a minimum, are not very far from dense in the real line. So a Poisson number is an algebraic integer that has exactly one conjugate outside of the closed, outside of the open unit disk. So all the other conjugates are in the open disk. And here's a sketch, basically how Salem's theorem is reduced to Salem and the rationality criterion. So if we have a limit of Poisson numbers with minimal polynomials, Pn, in particular for Poisson, this is where Poisson Salem numbers differ. The Poisson polynomials are non-reciprocal, so it is it's not a trivial operation to take the quotient of the function by its reciprocal. This would be a Blaschke product that preserves the disk, and by construction it has integer coefficients, so that's a formal function, of course, rational, and it has a single meromorphic pole at the reciprocal of the Poisson number, but all the other poles are outside of the disk. So we're going to apply Salem's criterion to a limit of these functions. Precisely, we need functions of bounded characteristic. Well, these functions have bounded characteristic. One can check that if we take out a residue at the pole, we have a bounded function on the disk. And so this sequence form a normal family, we can extract a limit. But on the level of this power series Fn, if the coefficients were integers and you have a limit, they have to stabilize also to an integer power series. And so we get in the limit an integer power series, which lies in the intersection of integrality and analytic conditions. And one, of course, so once we know this is rational, it's easy to conclude that it's of the form Q over Q star for some other Poisson polynomial. And here's another application. So this is what I will refer to as the square root method for proving certain type of separation of algebraic conjugates, which ultimately, I hope in some weak form, it eventually works for zeros of L functions. But for polynomials, this is not surprising. Algebraic quantities have the Liouville bounds and various others related to integrality of discriminants, resultants, and so forth. And so here is the statement. the method. So an application of Pouillat's rationality theorem. Let's read it in the contrapositive. So suppose we have a function of the form square root of a polynomial, but suppose this polynomial is not a rational function, so it's a quadratic irrational function. And suppose this polynomial, so the square root function has integer coefficients. And well, then Pouillat's theorem tells us that if the function is holomorphic on the complement of some set E, let me apply Pouillat's theorem with 1 over x, so that I center this, so p of 1 over x, and then taking the square root and centering at the point infinity. But if this function can be extended holomorphically to a complement of E, then E has to have capacitance at least one. It has to be large by Pouillat's theorem. But observe that because this is a very special kind of construction, square root of a holomorphic function will be holomorphic on the complement of any set E that, like, for example, whose components are Jordan arcs, each of which contains exactly 2 of the roots of P, of 2 of the singularities, for monodromy reasons, right? Any loop contained in a complement will encircle an even number of those singularities. There is no monodromy around the loop. And the observation of the following application is that the condition is always fulfilled for polynomials of the form q2 times q4, which means start with any integer polynomial with q0 equals 1, and take the polynomials whose roots are the squares or and the 4th powers of the roots of p, then this condition is in place, the integrality of the square root. And so this leads to solution of the following problem. Basically, that gives the best structural lower bound on the house of algebraic integer, largest absolute value of conjugate. So of an algebraic integer, which is, this is a union sign, of course, apologies. So it's not 0 or a root of unity. There are, so at the same time, it gives, it's not, I don't think this is really about so much about the Lamer problem. It gives other results, applications, which are also optimal in a way. There's not something about Mahler measure. So for example, this argument also gives the optimal separation bound about 2 Salem numbers in a fixed interval, or 2, maybe 1 numbers, both of which are either Salem or Pizot. So I already introduced Pizot numbers. Salem number is the condition for the reciprocal counterpart, that we have like 2 conjugates of the circle, but all the other ones are on the circle. And we can construct, for example, starting with your favorite. So this is the Pizot polynomial with smallest root. So these numbers are isolated. And take this polynomial, take its reciprocal here, and for any power, after taking out the root of unity factors, for large enough power, this number will be, this polynomial will be Salem. And so this construction incidentally shows that I have, if you consider the roots of this polynomial with rowing k, well, by the equation that they satisfy by this definition, they clearly converge at an exponential rate, like roughly lambda to the minus n, where n is a degree and lambda is this Pizot number, I guess rho in this case, to the Pizot number itself in particular. Within each other, they are at an exponential separation. So the previous argument also shows that this is best possible. So if you take numbers in the interval 1 to L with degrees at least n, at most n, which are Salem or Pizot, they have to be, and are not equal, they have to be spaced like this exponential. And the usual Mahler separation bound, or anything else that I know of that uses somehow Galois conjugates and some norm, or the Galois group, broadly speaking, is exponential in minus n log n. So this case is, again, we form a suitable quadratic function like this square root using the P2 and P4 operations. But now I've added also, I aim for separation bound for lambda and this other lambda prime. So I take both of their minimal polynomials, multiply them in this construction. And for the set E, suppose, well, basically we can take if lambda and lambda prime are close, the actual Salem numbers, I take the pairing, then the 2nd and 4th powers are also close. And the other conjugates don't really matter so much. I can join them. They're all within the circle. I can use like a contractible star pointed at the origin to connect the other conjugates, or I can pair them suitably in pairs. In either way, for the set E defined in such a way, this f of x belongs to these like things I try to call rings of regular functions on formal analytic arithmetic surfaces that have that are pseudo-concave. In this case, this definition is the capacity. The set E is small enough for. So in this sense, it means capacitance of E is exactly less than 1. In that case, we have a contradiction with Poyar's theorem. But a simple estimate shows that, like, if this lambda prime are more than this exponential bound that I stated, this capacitance is less than 1. So this is basically a separation bound viewed in this way. And of course, so this is the usual thing that was Adamar's inequality, and Malek's discriminant bound is included here, Malek's separation bound, and eventually for multiple points, I mean, in this version, it's a Mignot's separation bound. This inequality is elementary. Okay, so some kind of Adamar inequality on a van der Monde matrix after column operations for complex polynomials. And usually if you have, well, if we have an integer polynomial, one says that the discriminant term has to be positive, one drops it by positivity, one loses in this argument because discriminants are rarely small, so much smaller than like d log d or so, and we estimated it by 1. And here is another example that actually is the shift to the second topic of L functions. But this is about Veil polynomials for Frobenius roots. So it's still a local story. So it's a statement about polynomials, which also gives the best separation bound. Consider abelian varieties over FQ, abelian varieties of isogeny, okay, Veil numbers of an even dimension, say 2G, so that maybe the case I will consider have in mind could be that A is the product of 2G dimensional abelian varieties, but that doesn't have to be necessarily like a product. But I want to take the dimension to be even, so that so now the Frobenius roots are a conjugate set of algebraic integers, Galois table set, contained in the circle of radius square root of Q. And on that circle, I want to pair them with circular arcs in the smallest way. And the smallest way, let's say, would be by considering the total arc length covered. If the abelian variety is not isogynous to a square, then how, so in which case, of course, we can just like, we have double roots, then there has to be some separation bound on general principle. And the question I propose here an answer with the Poyar's theorem, with the square root method, similar construction, is what's the optimal separation bound that we can prove. So in the asymptotic of fixed Q and G going to infinity, this type of bound is the optimal exponent. For comparison, Malek-Mignot gives something kind of similar, but with a worse exponent. And I don't know if I would be very curious and couldn't see how much this bound improves when we have a curve instead of an abelian variety. That may be more properly analogous to the L functions case that I'll take up. But since we have roughly, exponentially many curves like up to isogeny of a given genus, and rather than quadratically many for abelian varieties, so one accounting heuristic would suggest that it's hard to get a separation bound that's smaller than that's little of 1. So the proof is so the same square root construction. I didn't have to worry here about the two-adic congruence. Let's just make the two-adic conversion by using a factor of 4 by hand. So this square root function has integer coefficients. And because the alphas and betas generate a CM field, one sees that it's also Galois. I mean, these traces to R are also a Galois stable set. And so this has rational integer coefficients. For the set E, we get a beta bound after we project to the traces, project from the circle to the line, minus 2 squared q to 2 square root of q, and which is why I take this E in Poyas theorem to be after the factor of 4. It's basically the projection of the union of arcs. And I want to relate this arc length to the conclusion. Basically, at this point, Poyas theorem tells me contrapositively, it's already a separation bound for K. K cannot be, for apologies, this E. E cannot be too small in the sense of transfinite diameter. The transfinite diameter is at least 1. And the rest of this estimate relates the questions, which basically, the notions of size, which basically asks how small can be the transfinite diameter for configurations that are unions of a given number of arcs on the circle. So there is a simple relation between the transfinite diameters of E and this original set of arcs. And so again, this inequality capacitance of E, apologies for writing K, is at least 1. It means that the original arcs on the circle have a capacitance bigger than roughly q to the 1/4. So there is a theorem by Haliste about one can certainly compute the capacitance explicitly for a union of circles that is rotationally symmetric. If you keep a given arc length L and you have 2 G arcs on a circle, let's say on the unit circle, which one will maximize this transfinite diameter? The case is, this case has exactly this, after the normalization, it's this transfinite diameter, and this is an upper bound on the capacitance of E, a lower bound is as before, and so this more or less translates into the sharp bound that I had, this bound with the exponent minus g minus 1/2. In L functions, I'll think of n to the the conductor to be like q to the g, and let me at this point try to connect to, I will pose one possible way to prove a little bit of the same spirit in for some L functions, but there may be other ways, and it's not very obvious if or should the previous result have a clean counterpart for true L functions, but just as the automorphic L functions are, okay, so they are entire meromorphic functions of order 1, and one thinks sometimes of their zeros in the complex plane as, by analogy, they would be compared to the zeros of L polynomials, but those are Galois orbits of algebraic integers. And of course, we have no Galois group and anything like that. And yet, some of the structure of a very transparent structure of polynomials, like factorization into minimal polynomials, irreducibles, disjointness of the Galois orbits, and things like that, have some tantalizing hints of, for example, in the ground simplicity of zeros conjecture and things like that, building blocks being like the Riemann zeta function, Dirichlet functions to the other characters, the L function of a simple abelian variety over Q. But in some sense, my point of the transition from power series and this discussing these separation bounds is that the arguments never actually used the Galois group anyway. They used the function itself, and it's like some square root operation on the power series and some ways to get analytic continuation and the integrality of the coefficients of the functions. Well, yeah, at least those types of things we certainly have in motivic L functions. The coefficients are integers by design, and should algebraic, these kind of algebraization methods be able to recognize L functions by the intersection of some analytic and arithmetic properties in terms of coefficients and analytic continuation. And would there be a version of capacitance, this notion of size, for extending through the set for Dirichlet series? So observe that in the end of the day, if the L function is modular, it comes out as the Milin transform of a modular form of some weight and level. And then this completed L function has the functional symmetry. I guess this k minus 1, what was the motivic weight. So the symmetry with this normalization is that s goes to k minus s. Well, we can, it's easier to try to recognize not the modularity of the L function as such, but the modularity of the form f. And the first step for that would be to prove algebraicity of the form f over the ring of modular forms. For that is actually enough to for proving that f is a modular form. And so the start of this discussion now is a continuation of a joint work with Frank Calegari and Yunjing Tang that was what was called the Unbounded Denominators conjecture, and contrapositively call that Unbounded Denominators property of modular forms on non-congruence groups. And all these Q series from the L functions database that we are familiar to, some of us on a daily basis. So they have integer coefficients, and the reason is perhaps of course, the Eichler-Shimura relation, broadly speaking, the Eichler period cycles and the naturality of Hecke operators, but all of these actors completely evaporate in the case of finite index subgroups of the modularity group that doesn't contain gamma of n for any n, and which of course are the majority of groups. And in this paper, the original statement of the conjecture was that if you have a Q series, which is a modular form for a finite index subgroup, but also has integer coefficients, and it extends through the cusps of the group. In fact, it's a modular form for some gamma of n, but actually assumed, sorry, I should really write gamma of n, for some, for the congruence closure of gamma. But it turns out more natural, perhaps, to view this theorem in terms of the L function, the formal Milin transform of f, and not so much of the finite index subgroup, because as it turns out, the theorem is still true for any thin group, for any Zariski dense, but thin group like it could be generated by just two matrices, 1, 1, 0, 1, 1, 0, n 1, which has congruence closure exactly gamma 1 of n. But having modularity in the thin group, where there's essentially just one relation, is just an expression of the functional equation of the L function of the Milin transform. And so, okay, this is still no mathematics, the daydreaming stage, but display the actual theorem very soon. We have, of course, converse theorems are the way to analytically recognize an L function through its functional equation. For example, Hamburger's, indeed in a form more precise that I have written, or Hecke with the condition that I highlight of bounded growth in vertical strips. So I've written the functional equations for the Riemann zeta function or for the function, this L function Ls chi. And if this equation is valid throughout the whole complex plane, so that, that assumes that both sides extend. They were initially defined as Dirichlet series convergent in some right half plane, and then f of s has to be a scalar multiple of the known solutions. This case, of course, is particularly simple because the group gamma 0, well, the modular group is generated by just the two standard matrices, and there is no need to use veil character twists. But the thin group in general just uniformizes a disk minus two cusps, and there are infinitely many solutions to the naive equation, functional equation with coefficients in C. In functional field arithmetic, on the previous discussion, this can be considered like this type of functional equation without the gamma factor, which has obviously certain polynomials as solutions, polynomials imputed to the S with a certain reciprocality condition. But the question may be, even in these basic examples, this is a question I can't quite answer satisfactorily, but prove some effective bounds towards that. So what are the closed sets in C for which this characterization by converse theorem persists even if we assume the bounded in vertical strips of both sides on the complement of some closed subset of the critical strip? So as you may imagine, the kind of thing I'm usually thinking of is to have some, if we have, for example, a square root construction and the set K would join certain pairs of zeros, but abstractly, let me ask it in this way. And so, for example, if we take K to be symmetric under the complex conjugation and the involution 1 minus S, and then we are just positing this functional equation, but assuming only the sides are holomorphic functions, single valued on C minus K, bounded in vertical strips. So this is very different from having like meromorphic poles or something like Artin's conjecture. They are definitely, they blow up at the meromorphic pole, and Riemann's removable singularity theorem is definitely not about meromorphic poles. So finally, we can make a naive translation between the power series language and the local zeta functions language with this x equal to q to the minus s. And then we can state Poyat's theorem, which was characterizing polynomial rational functions by such analytic properties in terms of this like complex variable s. We can just take the capacitance in the usual sense of the image of the compact of the closed set K under this map. And if this capacitance is smaller than 1, then we have shown that f is a rational function of q to the minus s. This is just rephrasing the theorem. Somehow a necessarily vague question at this point is that, is this naive translation pointing to a statement that one can try to approach for true L functions? So in what sense can one has these gamma factors appearing in the functional equation, and does Q equal to E in the capacitance theory, or is the one relevant notion simply to take the like image under the exponential map of your closed set K and then take its capacitance? And so concretely, if you take this L function like Dirichlet character chi minus 3 with just coefficients say minus 1, 0, and 1, and look what are the sets E of the disk of radius E for which we still have the Hamburger characterization of this L function by its function equation, but only assumed on a complement of the log logarithm of this set E, which is bounded on every disk wherever it is defined. So, for example, just to say to state the obvious, if this set here had just like usual capacitance 0, then by removable singularities theorem, this is certainly true. That uses no arithmetic dimension. But can we? How much would the situation improve if we take into account the integrality of the Dirichlet series coefficients? Let me perhaps, yes, I will skip this slide and now finally state some mathematical statement. This is the integral converse theorem, which answers qualitatively, it gives a qualitative answer to this question. So basically, this is the case where the set E is the empty set, and we consider functional equations of the GO2 type. The content of this theorem is that no Dirichlet series twists are necessary if the Q series has integer coefficients. So this is the generalization I'll spell out. And we only need to know one functional equation. So for instance, the modularity theorem for elliptic curves over Q, the conjecture of Shimura and Tanyama turns out to be covered by the earlier Hasse conjecture about the existence of a functional equation with of the L function. So the statement is the following. So let's, for some flexibility, consider any number field K and a finite set of places, but consider just one distinguished complex embedding And I want to consider series with almost integer coefficients. That could mean, for example, that there are S integers, but also all the V-adic convergence rate, they converge V-adically on the open unit disk, open, not closed, for each V, including the primes in S. So some mild denominators don't hurt. And we take under this one complex embedding the formal Mellin transform. I mean, just taking the Dirichlet series coefficients to be given by AN under that complex embedding. And we suppose the good analytic properties for this, we can be loose about the second side, this F tilde, the companion in the function equation. In the end of the day, it will turn out to be just like F acted by the weight K freak involution. But the setup is this. Suppose that there are some integers N and K, such that we have there exists, so firstly, this Dirichlet series converges in some right half plane and has a companion with complex coefficients that converges in some half plane, and such that the following equation is true and like bounded in vertical strips on the whole complex plane. So are this ring bounded in vertical strips. Then F is indeed a classical modular form of this weight K in the functional equation and that conductor N. And F tilde is its, how do we say, Fricke companion. And so in the case of, so how does that reduce to, and try to bring, spell out 2 points. Firstly, that the previous problem was about how much can we relax this condition about all of C to just some complement of some sufficiently small closed set in the critical strip. And for example, it could pair up some zeros and L functions, and the what quantitative and effective conditions we can say that is small enough for that to be the automatic extension through that set. And second, it is essentially an algebraization statement. So let me try to explain why this reduces in the end of the day to the unbounded denominators theorem, the unbounded denominators property. If we can find any finite index subgroup gamma for which the F is modular, then this integrality of coefficients means, well, that is exactly saying it's modular for some congruence group. And this means that we have a standard L function. But what does it mean to be modular under a finite index subgroup? Such a finite index group will emerge from a Fuchsian uniformization of a covering of the of Y of 2, which is just the triply punctured projective line, if we can prove algebraicity of the form over the ring of modular forms. And this is something that reduces to weight 0. Just, of course, we can just scale by our favorite weight K form, the reciprocal whose reciprocal has integer expansions. So it is a property about, well, the problem is about algebraicity of a certain type of integer power series. And those power series are already on the borderline of these criteria that we have discussed. So let me give a statement. This is like a non-multivalent extension of Pouillat's theorem. In this precise form, it was supplied by Bost and Shaw in their monograph. And our approach to unbounded denominators conjecture proved a weaker form of this estimate. And also observe that, so let me try to spell out also how this contains Pouillat's theorem. For any holomorphic mapping of the closed, some neighborhood of the closed complex unit disk to C sending 0 to 0. And this is by like ampleness condition that this mapping, this is like the domain, but now it's like a multivalent domain. It's a mapping, has derivative bigger than 1. Without this condition, there is no conclusion. There are continuum many such formal functions. But if this mapping has derivative greater than 1, then the field of meromorphic functions on the formal analytic arithmetic surface, that means simply, which is to say that we glue a formal scheme to the disk using phi inverse as a gluing map. Okay, concretely it means that this is the field, or I should say the fraction field of the ring of integer power series whose pullback under the analytic mapping phi is holomorphic on the disk. So the interplay with the integrality and the analytic continuation condition. So the theorem is that this is under this condition of pseudo-concavity, this is a finite extension of the rational functions, and the degree of that extension is explicitly bounded by this type of integral that we called holonomic quotient, or some kind of quotient, which is like because we can view this like some kind of a sheet number about that measures the multivalence of this mapping. If the mapping is injective, it's a univalent mapping, then this quotient equals 1. So this, by Jensen's formula or some version, so this contains Boyar's theorem and extends it to a multivalent mappings. And it gives a handy criterion in situations like this to approach algebraicity of a formal function. And how can we do that when we have some formal function already on the borderline? We have the trivial map phi of q equal to q on the unit q disk, the analytic coordinate, and that certainly defines a holomorphic function, but the disk is just barely, just like on the borderline. And if we can get any kind of overconvergence, like a different map phi with a bigger derivative that still has analytic pullback for the formal functions, that would give us the algebraicity. One can, in general, this idea, well, is familiar from the Apéry rationality proof for zeta of 3, for example. The idea is that you can take a modular form and express it in terms of a half model or modular function of weight 0, and the result will be a holonomic function, will satisfy a linear differential equation with constant coefficients of these kind of things that come from modular forms. And in Apéry's proof for zeta of 3, the sequence of rational approximations to that number came via this kind of change from a simple modular forms construction as was interpreted by Beukers. In this case, let's take the following modular function, which is now, so this is the modular lambda function, and x, this modular function will have the following equality of rings. So we preserve the integrality. So there is some kind of formal analytic integral structure behind. But we can just discuss it on the level of q expansions or x expansions. They preserve the integrality of coefficients. But now in the x coordinate, we have holonomic functions, broadly speaking. So this x is a local uniformizing parameter at both cusps of this thin group. So we start from the functional equation of the L function, which is just the assumption of modularity of f under just one transformation, this Wn, of course. So this group, maybe Wn corresponds to a group which contains this with index 2. But okay, in any case, this quotient parameterizes a disk minus 2 points. And at both of these cusps, we have a local parameter. If we choose the map phi to be universal covering map of the disk, let me try to describe it like that. So somehow our setup was already on a borderline where the criteria almost but not quite applied, and they were, if now we uniformize this disk as like disk minus 2 punctures, where some p of n, which is kind of intricately depending on this n, then one of the cusps, the origin of the disk, is the center of the z series. Is the analytic coordinate of the disk, or the q series, or the x series. If we fill out the second disk, we can find a larger mapping phi by Schwartz lemma factorization through the universal covering space. It will have a strictly bigger derivative of the Sealy map, which had already derivative 1. And that would put the algebraicity task into the scope of this holonomy bound or algebraicity criterion, now that this pseudo-concavity condition would be in place. And as an application, consider, so again, the ground simplicity of 0 suggests that for L functions of simple non-isomorphic abelian varieties, firstly, the zeros should be simple apart from, of course, the central point, whose order, the order of the zero should should match the rank of the Mordell-Weil group. But apart from that point, the zero should be simple and disjoint, like for Galois orbits of algebraic integers, which we don't have here. And this type of statement completely trivializes the following theorem, but it's some concrete consequence of the integral converse theorem. If we have an abelian surface over Q, which so relating to the property that sometimes you can have these L functions of abelian surfaces that are squares in terms of like Euler products, and that doesn't mean that A is isogenous to the square of an elliptic curve, but changing the meaning of square. If now we consider the square to be square as a holomorphic function, the answer is completely different. And so this corollary states, so the squares, abelian varieties isogenous to a square of an elliptic curve are exactly those whose conductor is a square and whose L function has a holomorphic square root, is also a square in this complex analytic sense. Because the square root of Dirichlet series with integer coefficients and starting with term 1 has almost integer coefficients. It has certain denominators of 2, which was why the statement of integrality was relaxed in the main theorem. But it will be still, when it's turned to a Q series, the it meets this almost integrality requirements. And of course, the functional equation would be preserved in this setting on the square root of a functional equation. And so I don't have, I think I have like 3 minutes left, which I will focus on the connection. Okay, let me at least try to say, why do I put a price on somehow extending, allowing for some set E in the statement of the integral converse theorem? If that is true, for example, consider the class number 1 problem as approached even before its solution by Doiring and then Heilbronn. So of course there was solutions given by Hegner, Stark, and Baker, but even before that, Gelfand and Linnik almost got to a solution, except that they failed to notice that a composite auxiliary level would have reduced their application of linear forms in logarithms, some Diophantine analysis, to just 2 logarithms that Gelfand could handle at the time. And now, but somehow, what Doiring did in his paper in 1933, he looked at this whole, okay, he had just a trivial twist, but the L function and the zeros of the L function under the class number 1 assumption in the whole complex plane, particularly on the critical line, rather than at just the point s equals 1 that reduces with special values formulas to some Diophantine analysis. So basically, in this, just to simplify, this is a long solved problem, but suppose that we have a class number 1 field. That means that the Dedekind zeta function is equal to the zeta function of the principal quadratic form. And in many ways, this just means, for example, just take the series as a Dirichlet series. It's close when D is large to its n equals 0 part, which is just the Riemann zeta function at 2s, and so are the character twists. They are just the same principal part. But this naive analysis also carries through to the layer of the analytic continuation of the Eisenstein series, which is like on the whole plane. And there is the composition zeta equals A plus R with a primary term A, which is explicit. And depends very little on a twist if you twist by Dirichlet character, and the error term R, which decays very fast because of Bessel functions decaying exponentially in -y. And if we have, so this is how the twist will look like by psi and the class number 1 assumption, where this principal term is basically unchanged. It depends on the character only through its modulus. And if we take 2 different characters, psi1 and psi2, of the same modulus, but non-principal, real, even like those guys of modulus 24, and the following square root of a product of 4 Dirichlet functions. That's the shape of the functional equation that the GO2 type L functions have, and it would fit into the integral converse theorem if the set E could be included there. And Döring's analysis shows that the set E in this situation can be as small as just like E could be a union of disks of exponentially small radii in minus square root of D, and these estimates are effective. At this point, I'm out of time, so I thank you for your attention. Apologies.